let's say that we're given a spherical shell. Right, we've got a sphere. We can make it a little fancy, give it a little shadow if you want to. It's a shell, right? And it has uniform thermal conductivity. Now we're going to draw this in a 2D shape because, yeah, why not? It's got an inner radius of 1 meter and an outer radius of 2 meters. The inner radius temperature, Ti, is equal to 100 degrees Celsius, while our outer radius temperature is equal to 0 degrees Celsius. We want to find the temperature at 1.5 meters. Now that's not at 1 or 2 meters, it's at 1.5 meters. So we don't know the temperature because we don't know the temperature. And you can't just, bibbidi bobbidi boom, get the temperature. You might think that you can use the thermal conductivity equation from any of these problems that we did before. The dimensional heat diffusion equation, right, for a slab, or for the coffee cup problem, but no, you can't because it's a sphere, right? And the way that heat diffuses through a sphere is different than just shaped like a slab. What you'll notice is that these units are in radians, right? Because it's a sphere. So when we take our heat conduction equation, negative thermal conductivity multiplied by the rate of change of temperature with respect to distance, this is in meters. Radians are not in meters. We can't use this. What we can use is negative thermal conductivity at the rate of change of temperature divided by radians. And in this case, we'll also add the area, right? Because you still need the area. We were determining how it flows through the area. And the area for a sphere is 4 pi r squared. And so now we have the basis for our for our heat conduction equation, which is the thermal conductivity, negative rate of change of temperature over with respect to radians, multiplied by 4 pi r squared. So what are we going to do if we want to find the temperature at 1.5 meters? Well, we're going to switch around the equation, do a little some of this, do a little some of that, do a little bit, do a little this, do a little that. And we're going to flip it around so we only have to worry about the change of temperature. How are we going to do that? Well, it's a little division, subtraction, addition, as I said. Really, it's just division and multiplication. There's no addition or subtraction. And we get that the rate of change of temperature with respect to radians is equal to our heat conduction divided by negative thermal conductivity multiplied by 4 pi r squared. Multiply that, oopsies, multiply that r over, and you get this equation right here. And this is what we want, because that'll help us find the change in temperature. When we take the integral, we'll take it from the temperature at the inner radius to the temperature of the radius we desire, which is 1.5, at 1.5 meters. And we'll also use the inner radius to the radius we desire, 1.5 meters. So let's integrate this whole equation. We get Ti minus T at the radius we desire. We're going to simplify this so you can use it in any general problem. Is equal to, we've got a lot of variables going on. You don't need most of these. You can take most of these out. This heat conduction, not a part of the problem. This thermal conductivity, not a part of the problem. This 4 pi r, take it out of that integration, right? We're taking all this out of the integration. And we get, I'm going to simplify this to just Q so I don't have to keep writing cond. We get this little subsect here multiplied our inner radius to our outer radius, integrated to our inner radius and outer radius. And that's what we want to integrate. So our final basic equation is negative 1 over r plus 1 over ri. Kind of wrote that in a strange way, Could flip it around so it looks nicer, but I decided not to because that's not how I see it in my head. If we take our numbers right here and we substitute it into this equation, you'll find that we have multiple variables that we do not know, including this heat conduction and this thermal conductivity, or this thermal conductivity. So what can we do? Because if we know this temperature, the radius and we don't know the temperature at the radius we want, we don't know any of these variables right here, how on earth are we supposed to find the temperature at 1.5 meters? Well, we are given the temperature at the outer radius, and that is very important because we can use that to determine the general number for these variables. You won't know the specific heat conduction or the specific thermal conductivity, but the general number for this entire equation part, not the equation yet. Let's take this general equation and transform it into the inner and outer radius workings. So 100 degrees Celsius minus 0 degrees Celsius is equal to our heat conduction divided by our thermal conductivity multiplied by part of our area over 1 divided by our outer radius plus our inner radius. And that's going to get you some pretty little numbers over here. Yes, indeed. Take that 0.5 divided, and we get 200 is equal to our negative heat conduction thermal conductivity 4 pi. So let's substitute that into this equation right here. And now we only have one variable that we need to find, which is perfect. So 100, well, let's not do that. Actually, let's do something else first. So we have 1/3 multiplied by 200 is 66.7 up. And we're going to subtract our 100 over. And then take that negative and pull it over there. And we get 33.3 as our temperature at the radius 1.5. So, after learning this whole expression, we have come to the conclusion that at the radius 1.5 meters, our temperature is 33.3 degrees Celsius. And so what have you learned through this entire process? Well, you've learned that for a spherical shell, we cannot use the same equation as we typically do for heat conduction. Why? Because there's radians involved, and those do not mesh well with meters. It doesn't compute, right? You won't have the same units that you need. So instead, we can write it to a different equation.